Hello everyone, and welcome to this overview of assaying bispecific antibodies with your FIDA. In this video, we'll be going through the experimental setup as well as the subsequent data analysis. But first, a brief reminder on the terminology and FIDA assay setups, as we will be using multiple different strategies for this type of assay. A FIDA experiment measures the hydrodynamic radius of a fluorescent molecule by characterizing its diffusivity. Two important FIDA terms here are indicator and analyte. The indicator is the fluorescent molecules whose size is measured, and the analyte is the compound that is titrated. There are four ways of doing a FIDA experiment: premix, capillary mix, capillary dissociation, and capillary flow experiments. With premix, you have an equal amount of indicator and analyte vials, and all of the samples are premixed prior to injection. Using capillary mix or cap mix, you have a single indicator vial and a titration of analyte vials. Using this method, the samples are mixed in the capillary by the FIDA instrument. When doing capillary dissociation or cap dis, you have a titration of mixed indicator and analyte vials and a single buffer vial. The complex is then injected into buffer. Capillary flow experiments or CapFlex you can ignore unless doing liquid-liquid phase separation and condensate analysis. When setting up a ternary complex assay for bispecific antibodies, you can go about it in two ways. You can either A, make a rapid confirmation of the binary and ternary complex formation using only a few hundred nanoliters of sample, or B, characterize all biophysical parameters of your system in a single experiment. To do these experiments, one of your two antigens will have to be fluorescently labeled and the other native. In this example, we have done both and will demonstrate how to set it up and perform the data analysis. For rapid confirmation of ternary complex formation, we recommend that you perform a CapDis experiment. So your plate will contain many different indicator vials mixed with analyte and a single buffer vial. Ideally, for every bispecific antibody set you want to screen, you measure the size of your labeled antigen mixed with your unlabeled antigen. Then you measure your labeled antigen with your bispecific antibody. And lastly, you measure your labeled antigen in the presence of your bispecific antibody and your unlabeled antigen in excess. An example of such an experiment can be seen on the left. In this manner, you can confirm binary and ternary complex formation in 15 minutes and know the sizes of your complexes. No change to your standard FIDA methods are required, and these screenings can of course be performed as complete walkaway automation. Once you have measured the size of your complexes or identified an interesting bispecific candidate, you might want to do complete biophysical characterization of it. This can be done with a single titration on the FIDA yielding the size of your labeled antigen, the size of your ternary complex, the size of your binary complex, the affinity for your labeled antigen, the affinity for your unlabeled antigen, as well as the cooperativity of your system. This experiment can either be performed as a premix experiment or a capmix experiment. To reduce sample consumption the most, you need to use capmix, meaning you will be having a single vial with your indicator protein. In this example, 32 nanomolar of labeled antigen and many analyte vials with a titration of bispecific antibody and a fixed concentration of unlabeled antigen. In this experiment, the unlabeled antigen concentration was 80 nanomolar and the bispecific antibody was titrated from 0 to 2 micromolar. Again, no change to the standard FIDA method should be required. A theoretical example of how the curves will look can be seen on the left. At 0 micromolar bispecific antibody, only the size of the labeled antigen is observed. As the concentration of the bispecific antibody increases, the size of the complex increases up to the size of the ternary complex. As the concentration of the bispecific antibody further increases, all binding sites are eventually saturated and the size of the binary complex is observed. Once you have run your experiments on the FIDA instrument, you can analyze the data using the FIDA software. Going to the Data Analysis tab of the software, you can click the Load Data Files button and a Pathfinder window will pop up where you can navigate to your data folder and select the data you want to analyze. Once you have loaded your data, you can then evaluate the quality of your experiment. You select the time interval that will be fitted by selecting Data Start and Data End. If the baseline is drifting, this can be fixed by toggling the relevant tick. The noise reduction can also be toggled on and off. You fit your data by clicking single species or multi-species. In this case, there are 2 species, so we will use this fit. You can save the result by clicking the relevant button. This procedure is then applied to all data points. If you don't want to manually fit every last data point you have recorded, you can fit them all in auto mode. If you select auto mode, the top of the analysis software will change to an overview of the parameters that can be applied to your fit. You select the relevant fitting parameters, in this case a multi-species fit with standard settings. Click Load Data Files and go. This causes a pop-up where you can select the relevant files. Then the software calculates for a bit, and when it's done, it shows you the analyzed data in the Binding Curves tab. By clicking the Data Analysis tab, every fit the software has done can be manually evaluated and corrected. In this case, no corrections are required. Viscosity can automatically be compensated for by clicking this tab. Fluorescence area can also be seen by clicking this tab. To fit the data, you have to select the ternary complex model in the Select Model tab. When you do, you will see a pop-up asking for a few initial guesses for the parameters. The size of the indicator should be set to the data point at a concentration of bispecific molecule of 0 micromolar. The binary complex size is the end of the titration curve. The size of the ternary complex is the top of the titration curve. KD1 and KD2 should be set to the half point on either side of the top point of the curve. A good initial guess for the cooperativity is neutral, i.e. a value of 1. Lastly, you need to tell the software the concentration of unlabeled protein in your assay. You then click Apply and click Fit Binding Curve. In this example, we have fixed the size of the ternary complex, as we have already measured it in the initial screen, allowing for a more rigorous fit. The results are then displayed on the right-hand side of the screen. We see that this bispecific antibody has a very high affinity for both its target antigens and a slightly positive cooperativity. In this model, a cooperativity bigger than 1 is positive and a cooperativity smaller than 1 is negative. That concludes this video on ternary complex characterization with bispecific antibodies. I hope you found it helpful and enjoy your assays.